Oh, that's weird. Okay, lads and ladies, welcome back to MAC 1140. This is I'm still not used to seeing myself without the beard, but there it is. Today we're going to continue talking about what we've been talking about. So we've been talking about polynomials. Today is kind of our last day focused just on polynomials before we extend to the broader universe of rational functions. But as promised today, polynomials, specifically complex numbers and how complex numbers and polynomials interact with each other, and this thing called the fundamental theorem of algebra. Before I do that, a little word on the exams. The exams are in for the most part. There's a few of you for whom I have not gotten your final exam grades in. And that's because there's just a couple little issues. It's not something to do with you for the most part. If your test grade isn't in yet, it's because I'm trying to figure something out with the testing center or the written work. There's some sort of problem that I'm working on. So please check your Canvas messages, check the comments that I've left there. Make sure you respond to anything, like if there's a file missing or a file that I can't read, stuff like that. I think that's the only thing I wanted to say about those. Let me get some paper out, get the screen share on, and we can get moving. The test scores for your class were okay. They were about where I expect. The average for the whole class was about 65%, which is almost exactly where we expect to see it. So I don't have any issues there. If you want to talk about a specific test question, office hours is the perfect place to do that. There was no one question that like everybody bombed or anything like that. So there's nothing I'm especially worried about in that sense.
Could you repeat what the average was again?
I think it was 64 and a half, something like that. And that will change as I get those last little bits of stuff I need to grade those few remaining tests. It may go up a point or two or down a point or two, but mid 60s. I think last time I looked, 64.7, something like that. Okay, I've got a nice black pen. This is MAC1140. Section number is OR1. And that means we're talking about pre-calc. And today is October. What is today? The 11th? It's the 11th, right? Okay. So yeah, again, please do. Please do review the comments both on the exam assignment. You'll find some typed comments there, and on the written work. So I can I don't want to show you any of your classmates' stuff, but I can show you one of my other classes' stuff and give you a feel for what I'm talking about here. So if you look at the written work, that's where the bulk of the comments are going to be. You'll see. Well, let's get to one that was scanned nicely. I guess this person did so well, there wasn't a whole lot of commenting to make. But you'll see lots of stuff like this. I come in and make little corrections. If there's a place where you needed a little bit of help or there was something that was missing, you'll see lots of stuff like that. So they're just some examples. Don't panic, this isn't any of yours. But please take a look at these. This is where you'll find many of the most useful comments. The other place you're going to find comments is on the test itself. So if you come into the assignment just titled exam 1, like the place you actually took the test, you'll see typed comments there as well. So some of the problems lend themselves better to typed comments. Some of the problems, like the graphing ones especially, lend themselves better to written comments, and there are plenty of comments in both places. So please look at both places. The other thing, please check your Canvas messages and please check those comments on the exam to see if there's anything that I still need from you. So for some people, the scans weren't legible. For some people, a page was missing. For some people, there were pages that were like corrupted. The files didn't submit correctly, or when they were submitted or emailed or whatever was happening, the file became unreadable for some reason. So if especially if your test hasn't been graded yet, please look for messages and comments to that effect. That way we can make sure everything gets in. Even if your test was graded, please look carefully at that. I had one person in another class who submitted written work in 2 different places. He didn't realize that he had done that. And I of course did not realize until he pointed it out. And if he hadn't looked at the comments, then he would never have noticed that I said, hey, I don't have written work for these problems. Like, what the hell? And then once he pointed me to the other place where the written work existed, I was able to get in there and rescore those problems and give him more points. So that's something that you certainly want to make sure to be careful of. The other story there is also, please very carefully follow the instructions on the test. I know it's a little bit weird getting used to a new testing format, but there are detailed instructions there at the start of the test, and a lot of us didn't quite follow those, and that's to be expected to a certain degree. But if you want faster turnaround on tests, you want better results, you want grades quicker, you want better feedback, all of that, please follow those instructions. That helps me help you more effectively. All right, today we're talking about complex numbers, which I'm supposed to assume you are all comfortable with, but I know that's not the truth. And then we're going to talk about complex zeros or complex roots and the fundamental theorem of algebra. And in mathematics, when you see the word theorem, we're talking about, an important true statement. When you see the words fundamental theorem, that should be like a big red flag, right? This is a big deal. First, though, I just want to talk a little bit about complex numbers and make sure that we're on the same page regarding what they are and how we can work with them. So let's do that. Okay. So what are complex numbers? Anybody help me out a little bit? What is a complex number? Is it a number that is hard to understand or something else?
A number like with a square root.
Often we encounter complex numbers for the first time when trying to take square roots. What is it about the square root taking process that produces complex numbers?
They have an I.
Mm-hmm. Yeah, and in fact, that would be on its own a reasonable definition. Complex numbers are numbers that have an I. If we're being a little more specific, we would say these are numbers of the form a plus b times I, where a and b are real numbers and I squared is -1. Now that last thing is usually the first time you encounter these, it's not written this way, but I'm telling you this for a reason. Mathematicians don't like to define I as the square root of -1 because it turns out there's 2 square roots of -1. But this last guy, most people first encounter this by saying I is the positive square root of -1. But the nicer way to say that is that I squared is -1. Same thing, same thing. And I think it was Joyce who said that. As Joyce said, these arise most often when we're taking square roots, right? Out of like solutions from the quadratic formula, stuff like that. Anywhere you may end up taking a square root of a negative number, you're going to bump into non-real complex numbers. Now, before I move into the details and start working with these, I want to make a quick little statement, and this is something that shows up tricky wise. So sneaky fact. also lets us use some notation. The real numbers are a subset of the complex numbers. Complex numbers, by the way, are denoted you remember from the beginning of the semester, we have like the blackboard bold R for the real numbers, the blackboard bold N for the natural numbers, blackboard bold Q for rationals. The whole set of complex numbers is written with a blackboard bold C. And the sneaky fact here is that the real numbers are a subset of the complex numbers. What that means every real number is complex with imaginary part b equal to 0. So when you look at this definition, a plus bi, a is called the real part and b is called the imaginary part. And the sneaky fact here just says that you can write any real number in this form just with b equal to 0. So for example, 5 can be written as 5 plus 0i. Pi can be written as pi plus 0i. Right? Every real number is also a complex number. It's just a complex number whose imaginary part is 0. All right. What else do we want to say while we're here? We talked a little bit about the algebraic structure of the real numbers. The real numbers form a complete ordered field. Remember that from day one, complete ordered field. Complex numbers are a field. They are also complete. They don't have a total order. You can't put the complex numbers on a number line. In fact, if you want to graph complex numbers, like you can graph a real number by plotting it on the number line. Complex numbers are two-dimensional objects. So rather that we have the real line, and then the complex version of that is called the complex plane. And I'm going to show you some beautiful pictures in the complex plane a little later today. But let me just graph for you a few complex numbers. This is equivalent to like just plotting a real number on the line. So this part over here is called the real axis. And this part up here is called the y-axis here is called the imaginary axis. So if I want to graph the complex number 2 plus 3i, that's a complex number whose real part is 2 and whose imaginary part is 3. So here would be the complex number 2 plus 3i. It's that point in the complex plane. The number I itself, I guess I should call this 1i, 2i, 3i. The number I itself is right here. So this would be 0 plus 1i, or just I. The real number -2 is over here. This is -2 plus 0i. I think you're starting to get the idea, right? So like down here at the coordinates, say, if I'm at the coordinates 4, -2, what is this complex number? Down here.
Would it be 4 minus 2i?
Perfect. Yeah, Dave nailed it. 4 minus 2i. All right. So complex numbers, in the same way that real numbers live on a line, complex numbers live in a plane. That's just the only thing I wanted to emphasize here. This structure is very nice, right? You know, this is very similar to the XY plane. And it turns out that if you want to study complex numbers or functions of complex numbers, the geometry of the complex plane interlaces very nicely with the arithmetic and algebra of the complex numbers, such that like multiplication is like rotating, addition is like vector addition. If you've ever seen that, it's very, very beautiful. A lot of people prefer to work in the complex plane over working on the real line. In fact, there's this famous statement by, I think it was Halmish, who said the shortest distance between two true statements on the real line passes through the complex plane. Meaning if you want to solve a hard problem having to do with real numbers, sometimes it's easier if you think about the equivalent problem with complex numbers and solve that instead. Okay. So that's what complex numbers are. What do we do with them? How do they show up? So the arithmetic of complex numbers, we can add, subtract, multiply, and divide. The complex numbers form a field. Which means we can add, subtract, multiply, and divide complex numbers. And the only one, oops, sorry, the only one that's not obvious how to do it is division. Addition, subtraction, and multiplication of complex numbers works exactly how you would think it works. That doesn't mean I'm not going to show you an example or two, but I just want to say that division is the one that requires a little bit of cleverness. Good news is that we're not actually in this class. We don't need to divide complex numbers ever. Still though, let me show you how it's done, especially the addition, multiplication, subtraction. We got to do that.
Are we ever going to have to do that in future courses?
Oh yeah. Well, I mean, so after the calculus sequence, if you take calc classes, kind of the next step, there's sort of two natural progressions. And one of them is complex analysis. There's a course at UF called Functions of a Complex Variable, and it's a mid-level undergraduate course that is kind of thought of as Calc 4 for a lot of people. And there you'll be doing a lot more than dividing complex numbers. And other future courses certainly may require you to divide complex numbers. In my Calc 2 class, for example, I show lots of students shortcuts for things that are hard to do with real numbers, and kind of thinking back to that Helmut quote. Some things that are very hard to do with real numbers are much easier if you do them with complex numbers. And in those processes, you must divide complex numbers. It's a good thing to know. It's a good thing to know, but we'll go over it very quickly with emphasis on the first three, because that's what you will have to do. So let's do it. Let's form or perform the indicated operation. We'll do this in several parts. How about 3 minus 10i plus 7 plus 2i, and subtract some complex numbers like -5 minus I, and this one I'll put in some parentheses, minus 6 plus 4i, and then some multiplication. How about 2 plus I times 3 minus 2i. I'm going to do one more here. 3 minus I times 3 plus I. And then we'll do one division problem. How about 2 plus 3i divided by 1 minus I. Okay, so we're going to do each of these. the trick is you can treat I like a variable. The same rules apply, meaning like you can think of two numbers as being like terms if they have an I attached. So in the same way you would add 3 minus 10x plus 7 plus 2x, you would add these complex numbers, meaning you'll add the real parts, 3 plus 7, and you'll add the imaginary parts, negative 10 plus 2. So here's how I would write this. I would say this is 3 plus 7 plus 2i minus 10i. So just put the real parts together, put the imaginary parts together. 3 plus 7 on a good day is 10. And 2i minus 10i, in the same way that 2x minus 10x would be negative 8x, this is going to be negative 8i. Okay, not too bad. Subtraction works similarly. You just have to remember to distribute. So when you take one complex number and you subtract another complex number, you need to subtract both the real and the imaginary parts. So again, it works just the same way it would if I was a variable. You treat it the exact same way you would treat a variable. So I would start by saying this is 5 minus I minus 6 minus 4i, right? Distributing the negative. I distribute this negative to the 6 and to the 4i. 5 minus 6 is negative 1, so put the real and imaginary parts together. The real parts, 5 minus 6, and the imaginary parts, negative I minus 4i is negative 5i. Okay, for parts C and D, I'm going to move down. I'm not going to solve these right here because we don't quite have room, but I want to just make sure we're comfy with the basics first. Are there any questions about where any of these pieces are coming from? Don't be shy.
Isn't that negative 5? Would that be negative 11, not negative 1? Just so I'm not reading it wrong.
Here. Oh,
Yeah.
this is a negative 5, isn't it?
Okay,
Yeah,
okay,
yeah,
good.
yeah. I'm so
I
sorry.
thought I was
Excuse me.
losing it.
No, no, you're not. Nope, you're 100% correct. Yeah, this 5 here is negative, right? Negative 5. Negative 5. So that's negative 5 minus 6, which is negative 11. That's 100% correct. Thank you. Still early for me too. Yeah, that's exactly correct. Other questions or comments? Thank you, Sean. Okay, then let's take a look at these two products here. One of them is special. Let's come down. Part C, I want to look at first 2 plus I times 3 minus 2I. So when you multiply complex numbers from time to time, you're going to have to use the definition of I. Remember, I is on the one hand, you can think of the square root of negative 1, or it's a number such that I squared is negative 1. So if that was an x, 2 plus x times 3 minus 2x, you'd FOIL. And the same thing is true here. We're going to FOIL. So my firsts are 2 times 3. My outers are 2 times negative 2i. I'll just write that out, 2 times negative 2i. My inners are I times 3, or 3i. And my lasts are I times negative 2i. And they're both, one is positive, one is negative. So this is plus I times negative 2i. So first, just kind of follow your nose. The most natural thing is the correct thing. And now we're going to work with each of these. So 2 times 3 is 6. 2 times negative 2i, again, treat the I like a variable. That would be negative 4 times I. So it's minus 4i. And you have the plus 3i. And then I times negative 2i. Again, if we just treat the I like a variable, then that's going to be negative 2 times I squared. And only the I is being squared there, right? Not the 2, not the negative. So it's negative 2 times I, which is negative 2 times I squared. And this is where we remember I squared is negative 1. So this is 6 minus 4i plus 3i is minus I, combining those like terms. And then we have minus 2 times I squared is negative 1. And negative 2 times negative 1 is positive 2. Positive 2 plus 6 is 8. So this is 8 minus I. That's that complex number. Any questions on this? Okay, let's look at the other product here in part C, 3 minus I times 3 plus I. I said this is a special example, and it is. And you notice that there's some, these aren't just two random complex numbers. These two are related to each other. They both have the same real part, 3. And the imaginary parts are negatives of each other. These are called complex conjugates. So just a little bit of vocabulary for you. So in general, the complex conjugate of A plus BI is A minus BI. So if you change the sign of the imaginary part, or if you swap I for negative I, you get a special number called the complex conjugate of the first number. And these multiply in a neat way. We'll just do it out the same way we did above, but you'll notice an interesting pattern. So if we FOIL, we have 3 times 3, which is 9, plus 3i, those are your outers, minus 3i, those are your inners, and then negative I times positive I is minus I squared. And the neat thing here is that the middle terms cancel, they add up to 0. So you get 9 and then minus negative 1, because I squared is negative 1, which is 9 plus 1, which is 10. This number is related to something called the modulus of a complex number, or the size of the complex number. If I graph, how about an orange? If I graph 3 minus I and 3 plus I, here's 3 plus I. Down here is 3 minus I. So complex conjugates are always symmetric about the real axis, because you change the positive I to a negative I, that just flips you from up here to down here. And then the thing called the modulus of the complex number is the distance from the origin to that number, which in this case would be the square root of 10. And it's the same for this guy. So if you multiply a complex number by its conjugate, you get the square of the modulus, or the size, if you like, the complex number. Now, that's not something you need to know for this class. Again, it's just a cute fact. But the nice thing for us is that when you multiply a complex number by its complex conjugate, the result is always a real number, right? 10, this is 10 plus 0i. So this is a real number. And that's because we were multiplying 3 minus I by its complex conjugate, 3 plus I. So anytime you multiply a complex number by its complex conjugate, the result will be real. And that's something we're going to use to divide. And then the business with the modulus is, again, not something you need to know, but cool fact. There's notation for all this stuff, but again, you don't need that. All right, last one is the division. So first, are there any questions on the multiplication here? So we want to take 2 plus 3i and divide it by 1 minus I. And the challenge here, kind of similar to dividing polynomials, right? If I wanted to take 2 plus 3x and divide it by 1 minus x, that would require some like long division process. It's not super simple. You can't, there is no clean way to divide this by these and get an answer in the form that we want without a trick. And the trick is you multiply top and bottom by the complex conjugate. Remember the multiply by the conjugate trick from the beginning of the semester for difference quotients? The reason we call that the complex conjugate, the reason we call that the conjugate is because it's inspired by the complex conjugate. So in words here, again, the trick is to multiply top and bottom by the complex conjugate of the bottom. All right, and you'll use this certainly in differential equations, maybe in Calc 2, depending on who you have for Calc 2. But it's a nice thing to know. And I won't be making you do this in this class, but we'll just do it real quick here because I think I would be doing a bad job as a teacher if I didn't show you what it is. So the numerator here is going to be, remember, fractions always have the tops and bottoms in parentheses. This is 2 plus 3i times 1 plus I, and I'll deal with that in a minute. Let's just clean up the bottom first. So I'll go ahead and FOIL out this bottom. That's 1 times 1. 1 times I is plus I. Negative I times 1 is minus I. And then negative I times positive I is negative I squared. So the bottom here we know is going to be a real number, and that's what we wanted. That's what's going to allow us to write down this answer in a nice fashion. So what is that bottom? Well, the middle terms add up to 0 plus I minus I. So this is 2 plus 3i times 1 plus I divided by 1 minus I squared. That's 1 minus negative 1. So that downstairs is 2. All right, 1 minus negative 1 is 2. And then upstairs, now I'm going to go ahead and do my normal foiling business. So 2 times 1 is 2. 2 times I is 2i. 3i times 1 is 3i. And then my last terms there are 3i times I, so that's plus 3i squared. This is 2 plus 5i, 2i plus 3i, plus 3 times I squared, that's minus 3. All right, I squared is negative 1. So we get 2 minus 3, which is negative 1 plus 5i for my numerator. And all of this is over 2. So if I want to write this in that standard form, a plus bi, I can do that because the denominator is real. I can split this up as negative 1 over 2 plus 5i over 2, which is the same as negative 1/2 plus 5/2 times I. That's how you divide complex numbers. So the division is a little bit complicated, but addition, subtraction, and multiplication is not. So once you have some complex numbers in your hand, this is how you play with them. Where do they come from? Let's look at that. And also, what about raising them to powers? First, the powers. We'll look at the synthesis of complex numbers by solving some problems. But the last sort of little intro playing around thing I want to show you. These cycle every 4 powers. So what I mean by that is like I to the 0, anything to the 0 is 1. I to the 1, anything raised to the first power is itself. I squared, well, I squared is by definition -1, right? I is the square root of -1. So what is I cubed? And I'm genuinely asking, I'd like you to take a second and think about it. If I squared is -1, what is I cubed?
Negative I?
Very good, right? Because it's I squared times I, which is -1 times I. If you don't yet see why I cubed is -I, I want you to make a little star in your notebook and come back here. Right? Just write it out. I cubed is I times I, which is I squared times I. And I squared is -1, so it's -1 times I. Now watch what happens. I to the 4, that's I squared times I squared, right? Anything to the 4 is that thing squared times that thing squared, which is -1 times -1, because I squared is -1, which is +1. Same as I to the 0. This is what I mean when I said they cycle. I to the 5, well, that's I times I to the 4. And since I to the 4 is 1, this is just I. I to the 6, you can probably see where this is going now. A bunch of ways to do this. I could say that this is I times I to the 5, or I cubed times I cubed. Let's write it as I times I to the 5. I to the 5 we just saw as I, so this is I times I. I times I is I squared, which is -1, same as I squared. I to the 7, based on the pattern we've seen so far, what do you expect I to the 7 to be?
-I.
Yeah, right. We expect I to the 7 to be the same as I cubed. Well, what is it? It's definitely I times I to the 6. I to the 6 we just saw as -1, so this is I times -1, which is indeed -I. So you could tell me what I to the 8 is, what I to the 9 is. It all has to do with the remainder when you divide the power by 4. So let's play a fun game. What's the current year? 2021, right? What is I to the 2021? Where in this cycle am I going to find myself? So I can go ahead and just illustrate back up here. I to the 8. I don't even need to compute it. I to the 8 is going to be 1. I to the 9 is going to be I. I to the 10 is going to be -I. And I to, I'm sorry, I to the 10 is going to be -1, sorry. And I to the 11 is going to be -I. So it continues like this. Based on this fact that the powers cycle like this, what do you think I to the 2021 will be? We got a 25% chance of just guessing it right. But let's think a little harder than that. What do you think I to the 2020 is? What if we did this last year?
Would it be I?
Very good. Very good. I to the 2021 is I. For what reason? All right, you ready to see that Euclidean algorithm used again, this time for numbers? I to the 2021 is I to the 2020 times I to the 1, right? And I to the 2020 is divisible by 4, right? What is 2020 is 4 times 505? Yeah. So this first piece here, the I to the 4 times 505 has an I to the 4 in it, which means it's 1. So this is 1 times I to the 1, or just I. These make for fun test problems, just giving you some large power of I, something silly like the current year, and asking you to use these cyclic facts to compute it. Sometimes shows up on the test, sometimes not, it depends. But yeah, just wanted to show you imaginary numbers, complex numbers, very, very cool, very, very cool. This sort of cycling behavior is the origins of something called group theory, beautiful field of mathematics, its own thing that was inspired just by looking at powers of I. And then complex analysis, studying functions where the variable is allowed to be a complex number, is a massive field of mathematics used everywhere in engineering, physics, of course in pure mathematics, even in my own branch of math, which is number theory, where we work just with positive whole numbers. Turns out, if you want to answer questions about positive whole numbers, you better get comfy with complex numbers. All right, that's enough of this. Talk about these things all day, but that's not what we're here to do. I'm going to show you some computations with complex numbers in just a minute, where we're starting with a polynomial, but let me show you the connection to polynomials. This is the fundamental theorem of algebra. And with a name like that, you know it's important. Now, this might actually not come as a shock to you. Because of the way we have learned about polynomials, you guys already know that roots come from factors and factors tell you roots. But here it is, here it is. Every polynomial P of x equals an x to the n plus an minus 1 x to the n minus 1 plus a1 x plus a0. I should say every polynomial of degree n, like this, has n complex roots when counted with multiplicity. So like you have to do it in your homework where you list a root twice if it's a multiplicity 2 root. And I'll call those roots C1, C2, C3. Not 2, Cn. So there's n of them. And can be written in factored form as P of x equals, it's your book says it like this: a times x minus c1 times x minus c2 times x minus c3 all the way down to x minus cn. So this doesn't come as a surprise to us, probably because it looks exactly like we've been talking about factored forms of polynomials, and if you have roots. The big deal here is that a polynomial of degree n will have exactly n roots if you allow for complex numbers and you count with multiplicity. All right, so in the same way, x squared, I would say, has two roots, 0 and 0. That's what I mean by counting with multiplicity, right? Some polynomials, the reason this came as a big shock, the reason it has the name fundamental theorem of algebra, is because it was surprising, because for a long time, people thought that, you know, quadratics with negative discriminants didn't have any roots. If I asked you how many roots does x squared plus 1 have, today you would tell me 2. They're plus and minus I. But if you asked that question 500 years ago, the answer would be, even from the top mathematicians of the time, none. None. It has no roots because there's no real number I can plug in there to make that guy 0. So this was a big deal, and proving this is actually incredibly challenging. It's something that requires advanced calculus techniques, or if you want to get away without using advanced calculus techniques, requires very deep algebraic techniques, much harder. So your book breaks this into two different parts. They call it the fundamental theorem of algebra, just says that a polynomial of degree n has at least one root. And then the complete factorization theorem says if you have these roots C1 through Cn, you can write the polynomial in this way. But that's not how other people describe it. This is the normal way of describing the fundamental theorem of algebra. The big deal here is that the thing you want to work, the thing you know works with real numbers, also works with complex numbers. There's one more theorem that I want to describe to you, and then I guess two more theorems, yeah. Now remember, anytime you see the word theorem, it means that this is something that could be testable, right? So first, here's the theorem on conjugate roots. This says if x equals a plus bi is a complex, a non-real complex root of the polynomial p of x, then so is x equals a minus bi, its complex conjugate. In other words, complex roots come in conjugate pairs. Complex roots come in conjugate pairs. So if 2 plus 3i is a root, so is 2 minus 3i. This is going to be important for a certain subset of problems. Like you remember those problems where I said, you know, give me a polynomial of degree 4 having these roots. Well, I could, if one of those roots is complex, I could omit one of them. And you would have to use this theorem to deduce that the other one is a root. I'll show you an example in a minute. But this is important, so please remember this. If a plus bi is a root, so is a minus bi. Complex roots always show up in conjugate pairs. This means if you graph them in the complex plane, there's a lot of symmetry. I'm going to show you some of that later. Okay, one more theorem. So last week, as we were working through these factoring problems where we use synthetic division, once we arrived at a quadratic, we were pretty stoked because we knew what to do from there. What the theorem here says is that every polynomial with real coefficients can be factored into linear factors. I should say real linear factors times irreducible quadratic factors. In other words, there is no such thing as an irreducible cubic. Every degree 3 polynomial can either be written as a product of real linear factors or a real linear factor times an irreducible quadratic factor. An irreducible quadratic factor is just a quadratic that doesn't factor over the real numbers. It's a quadratic that has complex roots. Okay, and sometimes it's not obvious how this works. One of my favorite examples, let me show you because I don't, maybe I don't remember it.
Sticks.
This is fun, yeah. So factoring that over the complex numbers, that looks scary. You guys don't need that. Here it is. So yeah, okay, that's what I thought. All right. So for example, x to the 4 plus 1 does not look like something you could factor easily, and it's not. But this can be written as x squared plus the square root of 2 times x plus 1 times x squared minus the square root of 2 times x plus 1. You can check. If you FOIL these out, you will get x to the 4 plus 1. And it's not at all easy to come up with these factors. But the idea here is that there is no polynomial of degree 4 or 5 or 3 that can't be factored further. They can all be factored further. And the worst case scenario is that you end up with some quadratics which themselves don't have real roots, cannot be factored neatly over the reals. But let me show you. This particular example is pretty friggin' gnarly. The complex roots for this guy are not nice. And each of these is irreducible. Irreducible quadratics. And we could factor this further. I can actually write this as x minus c1 times x minus c2 times x minus c3 times x minus c4, where c1 and c2 are what you get from the quadratic formula. For the first guy, x squared minus the square root of 2x plus 1, and c3 and c4 come from the quadratic formula for the other piece, x squared, plus, this one's the plus, and the other one is the minus, x squared minus the square root of 2x plus 1. These numbers are not nice to write. They're big nasty numbers that come out of the quadratic formula. So I'm not going to do that for these particular guys, but it's an interesting example because even if you gave this, if you have a friend who's in like Calc 2 or differential equations, you want to fuck with them, ask them to factor this into quadratic factors. Tell them, well, there's a theorem that says it can be done. I promise you it can be done. Do it. And you'll see them slowly turn pale because it's very, very hard. However, it can be done. And the hard step is this, getting into the quadratic factors. From here, if you want these numbers, C1, C2, C3, C4, you just use the quadratic formula on each of these, which is something certainly you could do, but it's going to take some time. And there are better examples for us to play with to get a feel for this stuff. All right, let me do one more. let's factor p of x equals x to the 4 plus 2x squared minus 8. And we're going to factor it two ways. Well, no, let's factor this into, two ways, into linear and quadratic factors, irreducible quadratics. Then factor all the way to complex linear factors. So when I say into linear and quadratics here, I mean real linear. Right, so our theorem guarantees that any polynomial can be written as a product of real linear factors and real irreducible quadratic factors. And then the fundamental theorem of algebra guarantees that we can factor all the way down into linear factors if we're willing to work with complex numbers. All right. So we've got two tasks here. Do you notice anything neat about this polynomial?
It doesn't have x cubed.
Yeah, no x cubes and no plain x terms, only even powers of x. So a few things to observe. First, you could jump in with your rational roots theorem, and that will get you started here. So we could use the rational roots theorem on this to try and extract the real linear factors. There is a trick though. So option 1. Use the rational roots theorem to get started, to extract a real linear factor. And then we'd have a quadratic left over, a cubic left over, I guess, and we'd have to keep charging down that road. That's an option. Unfortunately, it turns out that this particular guy doesn't have any rational roots. All right, so given a problem like this, this is a viable option, and most of the time that would be what you do. So usually you'll do this. But this particular problem is insidious. So here there's an option 2, which is a trick. Because there are only even powers, we can substitute u equals x squared. And then we'll be able to factor this like a quadratic, go back through our substitution, and continue working. All right, let me go ahead and try the second option, because like I said here, the first option on this particular polynomial will not work, although it usually does for problems in this class. So if u is x squared, then x to the 4 is u squared. And 2x squared is 2u. Minus 8 is just minus 8. See what happened there? It's pretty sneaky. Little substitutions like this can sometimes really save the day. Now this looks a little weird. I've written p of x, but remember u is itself a function of x. Okay. So if I just handed you this thing on its own and said factor, what would you do? We look for two numbers that multiply to -8 and add up to +2, right? Do two such numbers exist? How does this factor?
U minus 2 and U plus 4.
Very good. So those two numbers are -2 and +4. So this guy can be written as u minus 2 times u plus 4. And once we've gotten through that step, now I'll just plug back in x squared. So this is x squared minus 2 times x squared plus 4. One of these is an irreducible quadratic factor. The other one can be factored further over the real numbers, but not over the rational numbers. Which one is irreducible? Which one has imaginary solutions or roots?
X squared plus 4.
Yeah, very good. This one is irreducible. How do we factor x squared minus 2? We've used this once before in the semester. Force factoring as a difference of squares, right? So a squared minus b squared can always be written as a minus b times a plus b. So, and x squared minus 2, well, that 2 doesn't look like a b squared, does it? The x squared looks like an a squared, but 2 is not a perfect square. It is, however, the square of something. If I want to write this as x squared minus something squared, what has to go in the parentheses? Two is the square of what number? What real number? Hint, it's irrational. No? Square
Root
root.
of 2.
Yeah, square root of 2. So we can write this as x minus the square root of 2 times x plus the square root of 2. The alternate thing would be to use the quadratic formula on each of these. So using the quadratic formula or that difference of squares trick on the first piece, I get x minus root 2 times x plus root 2. And then the other piece I'll just leave as x squared plus 4. These are my real linear factors. And this is my irreducible quadratic factor. How do you know if a factor or a polynomial in general is an irreducible quadratic? How do you know if a quadratic is irreducible? Does anybody remember that from like a college algebra or previous algebra class? Starts with a D. Ends with discriminant. It's the discriminant. I know x squared plus 4 is irreducible because I've seen it a million times, but if you want to check, to check if a quadratic is irreducible, compute the discriminant. Which is b squared minus 4ac. Remember, if b squared minus 4ac is negative, then your quadratic has complex roots, non-real complex roots, which is equivalent to saying irreducible. Irreducible over the real numbers. Okay, so that last line here is the first part done. This is the factor into real linear factors and irreducible quadratic factors. If I want to continue, so to further factor that lingering piece, x squared plus 4, you can use the quadratic formula. Just like we did with that one example last Wednesday, the 4th degree polynomial where we had to eventually use the quadratic formula to finish factoring. We can do that here. So his roots will be negative, I'll write it out, negative b plus or minus the square root of b squared minus 4ac all over 2a. Here a is 1, b is 0, and c is 4. So this is 0 plus or minus the square root of 0 squared minus 4 times 1 times 4. All over 2 times 1. The 0 is 0, so this is plus and minus the square root of 0 squared is 0, minus 4 times 1 times 4 is negative 16. And this is all over 2. And here's where we're going to start using the complex numbers. So what is the square root of negative 16? I think we'd all agree that negative 16 is positive 16 times negative 1. And then you can split up the square root. So I have here plus and minus. Square roots don't play nice with addition or subtraction, but they do play nice with multiplication and division. So I have plus and minus the square root of 16 times the square root of negative 1, all over 2. The square root of 16 is 4. The square root of negative 1 is I. And all of this is being divided by 2. And then 4 divided by 2 is 2. So this is plus or minus 2i. In other words, the roots are x equals 2i and its complex conjugate negative 2i. In fact, the reason complex roots always come in complex conjugate pairs is because of the way the quadratic formula works. Because every polynomial can be broken down into real linear factors from which real roots will come, and irreducible quadratic factors from which complex roots will come. And because those quadratic factors, we find the roots using this quadratic formula, the b over 2a part will always be the real part of the root, and then this plus and minus, this will always give you the imaginary part of the root. And so that's that plus and minus that shows up in the quadratic formula that proves our previous theorem, that complex roots always come in complex conjugate pairs. So now if I want to finish factoring p of x, I would say therefore p of x is equal to x minus the square root of 2 times x plus the square root of 2 times x minus 2i times x plus 2i. And these are all the factors. This is fully factored over the complex numbers. All right. I know there's quite a bit here, so I want you to take a second, make sure your notes are clear and clean. and see if there's anything you'd like to ask about, anything we'd like to look at a little more carefully.
Would this be on any upcoming exams?
Most definitely. Yes, exam 2 will certainly have problems like this. I'd like to say with the caveat that usually we'd get started using the rational roots theorem. All right, usually you wouldn't need to make this substitution, but it's nice to know that you can, and there could be problems, maybe on the test, maybe not, where you have to make a substitution like this to get started. Usually we would get started with our rational roots theorem to get the stuff like this out. It just happened to be the case that this factor here didn't have any rational roots. But this procedure where you you factor as far as you can using the basic tools and then use the quadratic formula to factor any remaining irreducible quadratic factors most definitely will be on the test. Okay. Other questions on what we've done here? Some punctuation here. All right, let's go in the other direction. Maybe I give you some roots, possibly some of them complex, non-real complex numbers, and say, find me a polynomial with those roots. So let's find a polynomial of degree 3 with integer coefficients and roots x equals 1/2 and x equals 3 minus I. Remember what integer coefficients means. I'm looking for whole numbers. I want my coefficients to be whole numbers. So that 1/2 is going to pose a challenge because, you know, this is not a whole number. So we're going to have to think of some way to get a factor with whole number coefficients in that root. And then the complex root here, 3 minus I, he's not going to give me a problem integer coefficient wise as long as I remember my theorem on complex conjugate roots. So here's how I would do this. Since 3 minus I is a root, so must be what? What other complex number is automatically a root if 3 minus I is a root?
3 plus I?
Very good. Okay, and then roots tell us factors, right? Thus, our polynomial is of the form P of x equals some lead coefficient, don't forget this, times x minus 1/2. This real root gives me that real factor, times x minus, and these inner parentheses are so important, don't forget them, 3 minus I. That's this root telling me this factor times x minus, again, little inside parentheses are necessary here, 3 plus I. And there's cause for concern. It looks like maybe these roots won't be or maybe these coefficients won't be integers because I've got a 1/2 here and I've got some i's here. I's are not integers. Several things we can do. What I would do is multiply this out and just see what sort of quadratic we get. And then I'll worry about how to fix the issue with the 1/2. Turns out this lead coefficient A is going to be a tool to let us fix this 1/2. Also, because it's just good practice, we need to practice multiplying polynomials out. Let's go ahead and do it. I'm going to FOIL these two things here. My firsts, x times x, it's x squared. My outers are negative 3 plus I times x. So I write it like that, minus parentheses 3 plus I times x. My inners are minus 3 minus I times x, written just like that, minus 3 minus I times x. And then my lasts is minus times minus makes plus. And then you have 3 minus I times 3 plus I. Okay, that's what it looks like when you FOIL out these two terms. There's complex numbers in there, that's okay, because we know how to add, subtract, multiply, and divide complex numbers. We don't need to be afraid of them. So I have A times x minus 1/2 chilling out front. Let's just see what we get in here. It's all the normal simplification rules. We're going to distribute and combine like terms. If I multiply x times 3 plus I get 3x plus ix. And then distributing this negative, I get minus 3x minus ix. Same thing with the next term. I'll have minus 3x and then plus ix, because minus minus there makes plus. And then we also have to clean up this last piece here, which itself requires a little bit of foiling, right? That's 3 times 3, which is 9, plus 3i, my outers, minus 3i, my inners, minus I squared. And you start to see that some things go, like this minus ix and this plus ix. It's minus 3i and plus 3i pair. Minus I squared, this is minus negative 1. We'll clean that up in the next line. So this is A times x minus 1/2 times x squared. Now what about my x's? I've got a minus 3x minus 3x. That gives me minus 6x. So now those are accounted for. The only other terms here, I've got a plus 9 and a minus I squared. Well, I squared is negative 1. So this is A times x minus 1/2 times, I'll stop writing this as brackets now, just use regular parentheses. I've got x squared minus 6x plus 9 minus negative 1 is plus 10. Okay. So at this line, I can see that this piece right here has integer coefficients, doesn't it? The coefficients here are real numbers and they are whole numbers. So this piece is good. This piece has integer coefficients. This piece does not. So the question is, what could I use for A to make this whole thing have integer coefficients? What would I like to multiply this factor by in order to get rid of that fraction 1/2?
2.
Very good. So P of x would be 2 times x minus 1/2 times x squared minus 6x plus 10, which is 2x minus 1 times x squared minus 6x plus 10. And if we want to multiply it out further, we could, but you don't need to. I would say at this step, I can see that all the coefficients will be integers, right? Because every number here is a whole number. We would need to get at least to this step to verify that. If you want to multiply it out the rest of the way, I'm not going to write down every single step. You'll get 2x cubed. You just distribute 2x cubed minus 13x squared plus 26. 26x minus 10. But either of these would be acceptable. Okay. Now, here's a fun question. Are there any other correct answers here? Are there any other degree 3 polynomials with integer coefficients besides this one that have those roots?
No.
It's an interesting question. So did we have an element of choice anywhere along the way here? Like I had to start by writing down these factors. There really wasn't any other choice there. But was there any step along this way where I made a choice that I perhaps could have made differently? Yeah, I chose to use a equals 2 because I wanted to get rid of this 1/2. I wanted to get rid of the fractions there. Are there any other choices I could have made for a that would work?
4.
4 or 6 or 8 or 10. Any even number for a would have worked here, right? Because that would have cleared out this fraction. So yeah, this problem actually has infinitely many correct answers. Kind of the simplest one is this one, right? The smallest lead coefficient we could have used here is 2, but we could have also used -4 or +26 if we wanted. All right. Again, this will be on the test, right? Where I give you some information about a polynomial's roots, and I ask you to find for me that polynomial. Definitely something that you can expect to see on the next test. Okay, how are we doing on time? 9:24. That means we are a little bit over time, right? So I'll go ahead and end it here. I have you guys from 8 to 9:15, right? Yeah, so this is a good place to end, and that is the end of our discussion on polynomials. So next time we're going to talk about rational functions, which are ratios of polynomials. If you divide two polynomials, what do you get? Turns out that sort of function, if you can do the division cleanly and get a polynomial, it's another polynomial, but maybe the division doesn't come out cleanly, and then you really have to work with that thing. This will be a place where we're talking about asymptotes, vertical asymptotes and horizontal asymptotes. We'll be drawing some fairly complicated looking graphs. So you may want to take a look back at any material you have from, say, college algebra about graphing rational functions. We'll be working quite a bit on that starting on Wednesday. I am going to post another homework today. It'll be short, just this sort of stuff, you know, factor into complex factors and building up polynomials with given roots, perhaps complex numbers. And then next time we'll talk about rational functions and then rational inequalities. So we're almost there to that second test. Remember, after we finish polynomial and rational inequalities, we'll be ready for that second test. So that second test is probably going to be late next week, like next Wednesday. So just keep that in the back of your brain. And if you have anything you want to talk to me about, I have an office hour this afternoon from 1 to 2 p.m. You can just message, email, Discord. You all know the drill at this point. That's it. Take care, lads and ladies.